All right, the Unit 3 FRQ review question 6. We've got, sometimes we think of this as like a general function question, or I could just think of I'm working with a piecewise defined function. But as I'm reading through these questions, I realize that these are all kind of throwback questions to Units 1 and 2. So I might need to go back and look at some of my notes or examples from Units 1 and 2. I know limits was Unit 1, differentiability Unit 2, although it certainly is going to come up in every unit. So, all right, let f be the function defined by f of x, and we've got a nice piecewise there. Does the limit of f as x approaches 1 exist? And justify your answer. So I can see how this could be confusing. But if the limit of f as x approaches 1 exists, the thing that must be true, sorry, I have a whimpering dog now in the background. The thing that must be true is that the limit of f as x approaches 1 from the left must equal the limit from the right. So in this piecewise defined function, notice that at x equals 1, we are given the function value of 3. So that middle piece tells us that f of 1 is 3, but I'm not going to use that piece for evaluating the limit, because if I think about like a number line, and I'm just going to put the number 1 on the number line, if I'm approaching the number 1 from the left, I'm approaching that number from values that are less than 1. Now, I'm also going to tell you that I have never seen a piecewise function written this way. Normally, the leftmost piece is on the top. So I'm surprised that these two things are where they are. I'm not actually sure if that was on purpose, but we're going to go with this function as it's written. So I want to be super careful here. All right, sorry about the whimpering dog. No, it's a barking dog now. All right, so this bottom piece, I'm going to use this as I'm as I'm evaluating the limit as of f as x approaches 1. All right, so the limit of f, and you have to use the correct limit notation. There is no excuse not to. It is literally modeled for us in the problem. So the limit of f as x approaches 1 from the left is equal to, so I'm going to use x squared plus 5. So 1 squared plus 5. I did the math in my head before writing it out. And that is 1 plus 5, which is 6. And then I must also show the limit of f as x approaches 1 from the right. And again, if I'm going towards 1 on the number line from the right-hand side, I'm going towards 1 at values of x that are greater than 1. We said from the left, I'd be coming from values that are less than 1. So again, I think it's odd the order in which this piecewise function is written, but I can't help but wonder if it was done deliberately to make us think about it. I didn't write the question though, so it could also just be a typo, but we're going to go with it. All right, so the limit of f as x approaches 1 from the right is 2 times 1 plus 4, which is also 6. So I need this information. I haven't answered the question yet, and I haven't justified my answer. So we could say yes. You could say the limit of f of x as x approaches 1 exists, or you could say the limit of f as x approaches 1 equals 6. And by assigning that a value, it is implied that the limit exists. If it doesn't, we couldn't evaluate it. We couldn't assign it a value. But I have not justified my answer yet, because I must take it one step further and say, because you can do b/c, that should be just fine. The limit of f of x as x approaches 1 on the left is equal to the limit of f of x as x approaches 1 on the right. Now we have justified it. That is the definition of a limit. And we did that very early in Unit 1. You would have to look through the spiral to see where that is. All right. So then in part B, we are asked if f is differentiable at x equals 1. So it's possible we're going to have to check two things here, but I would first check the continuity piece because we're already like 2/3 of the way done with the continuity piece. So let's think to ourselves first, is f even continuous at x equals 1? Because if it's not, then f is not differentiable there. So I've already established that the limit of f exists. However, I think our function f is going to fail that continuity piece because we said the actual function value at x equals 1 is 3, not 6. So if I think, you guys could also graph this in Desmos, or you could just graph 2x plus 4 and x squared plus 5 and put them on top of each other and think about where the number 3 is. But if I know, if I'm coming up at 1 from the left and I have x squared plus 5, I know that this is a parabola with a vertex at 5. So it's going to look like that on the left, sort of, more or less, maybe less. On the right of the one, I know I have a line, 2x plus 4. So again, my line would have like a y-intercept of 4, but it would start that way. And then the function itself, though, exists at 3 there. So this is a not great, but good enough sketch of what that piecewise function could look like. It's not my best parabola, but whatever. We don't need to draw that. I'm just trying to illustrate what's going on here. Now, since I did draw a picture, I should tell you that on an FRQ, if you draw a graph, it will not be considered. So you can draw it if it's helpful to you, but it's not part of a justification. Okay, so is f differentiable at x equals 1? We're going to say no. No, because f is not continuous at x equals 1. Now, that's not enough yet to earn all the points. We got to show how we know f is not continuous at x equals 1. Well, we already established that the limit of f as x approaches 1 exists, but that is not equal to f of 1. So that is the definition of continuity. And very often in class, we break it down into the 3 pieces. So like this must equal f of 1. Since we already established the left and right in part A, we could just use the two-sided limit in part B. All right, part C. Oh, we got this new piecewise g. Suppose g of x is this piecewise defined function where m is a constant, so not a variable, just an unknown constant. Find the value of m that will make g differentiable for all real numbers. So we know that our function g must be continuous in order for it to be differentiable. So before I even bother with the derivative, I think that I would just start with the continuity piece. So again, using the definition of continuity, which is in a box on page 5 of your spiral, but I'd like to look at the note that is under the box for my definition. I've got to use limit notation here. So again, in this type of piecewise where I have a does not equal to, well, that's going to give us the limit from both the left and the right of 1. So just think about a number line. Again, I know we kind of did this. If my number 1 is here, if I were to highlight all the values that don't equal 1, well, I might need to put like an open circle here. That would be everything to the left of the number 1 and everything to the right of the number 1. So that would be all of the values that are less than 1 and all of the values that are greater than 1. So we could have written this piecewise like the one above, and we would just have 4x squared minus 5 written twice for x minus 1 and x is less than 1 and x is greater than 1. All right, so I'm going to use the definition of continuity. but before I do that, I'm going to evaluate my limit. So my limit of g of x as x approaches 1 is, and again, I've got to use this. So that's 4 times 1 squared minus 5. So 4 minus 5 is -1. All right, so then I also know that my function g of 1, that its function value is m. I know m is a constant. So if I want g to be differentiable for all real numbers, it must first be continuous for all real numbers. And so for that to be true, it must be the case that g of 1 is equal to the limit of g as x approaches 1. And we already found out that that is -1. So by substitution, we know m must be equal to -1. So we didn't even have to take the derivative. And just a note, so we are officially done with part C of this problem. Oh, the whole problem, there's not a part D. Whew, thank goodness. Just a note for anyone that is still listening. If we were to take this derivative, if we did take the derivative of g, I'm going to go back to not knowing what m is. Y'all, g prime here, this is kind of an exception to the rule. G prime would not be piecewise defined, because if I take the derivative, I'm really just taking the derivative of this piece. So I would get, what, 8x? I almost wrote 8x minus 5. Don't do that. 8x minus 0, since 5 is a constant, so, or -5. I would get 8x as my derivative. The reason that m would not be involved in our derivative, or I wouldn't have a 0 there, is because, remember, when we take the derivative of a piecewise function, we drop the or equals to from our inequality. And in this piecewise function, the or equals to is like its own line. But I could have written that whole piecewise function differently. So when I take the derivative, I'm only using all the values of x that do not equal 0. All right, that is it for this one.